5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Keeping satellites jitter-free is actually much more important than you may realize for things like Earth observation and satellite communications. Our guest this week has a solution for that. It's Alessandro Stabile, and he's the co-founder and CEO of Magma Space. Enjoy.
My name is Raphael Rodkin. I'm the founding partner of E2MC, Earth to Mars Capital, a venture capital investor in dozens of space startups worldwide, among other roles I have, such as being a part-time podcast host. Just as a reminder, this podcast is for informational purposes only. It does not reflect any view by E2MC, and nothing should be taken as investment advice. Before we start, a quick favor. If you do enjoy this podcast, please leave us a 5-star review on your favorite podcast app, such as Apple or Spotify. It does help other people find the podcast. Now on to today's episode.
Hey, space enthusiasts, welcome back to another episode. My guest today is from Magma Space. It's their co-founder and CEO, Alessandro Stabile. Welcome, Alessandro.
Thank you, Raphael, a long-time listener. I'm really excited to be here with you.
Yeah, and for full disclosure, through my day job, E2MC Space Venture Fund, we are actually small and happy investors in Magma Space. You participated in our new Orbital Edge Accelerator program this year.
And I'm proudly wearing the sweater with the Orbital Edge.
Oh, let's see that.
So we're excited about this.
Well, I didn't see it. Can you kind of? Oh, that's very nice. See, I didn't even get one. Like, we run the program. Okay, I gotta follow up on that.
It was a great program, so we're excited to talk about this even later. But yeah,
let's do that. A little bit later on, if we have time, we'll talk a few minutes about Orbital Edge, which might be relevant for other space entrepreneurs and investors as well. But as a long-time listener, you know the way we usually kick this off is with you giving the elevator pitch about Magma Space, please.
Absolutely, yeah. So at Magma Space, we are tackling the issue of satellite instability that's really becoming a critical to a lot, if not most of today's and tomorrow's missions. Because every satellite vibrates, and it is due to this component called reaction wheel. Virtually every satellite has 3 to 4. And these tiny vibrations that in Europe are called micro vibrations, in the US are called jitter. They do affect and compromise missions. Think about imaging, where jitter can blur and conceal details, laser communication, where you can limit data rates, and a lot of the emerging space capabilities like power beaming, in-space manufacturing. There is a lot of talk about quantum sensing, quantum key distribution. All of these applications in one way or the other are affected by jitter. And jitter is also affecting the autonomy that you can achieve on your satellite, because think about jitter adds noise to your data that builds up error in the algorithm and ultimately produce uncertainty in the output. So you always need constant supervision and human in the loop. And jitter does break the trust in autonomy. So this is where we come in. We are building the autonomy and precision platform that truly unlock the next leap in satellite performance. And we want to achieve true trusted autonomy. And so we do this through a combination of hardware and software. From the hardware side, our breakthrough is in magnetic levitation that is initially applied to reaction wheel. And we've already shown that we can achieve more than 95% vibration reduction compared to whatever is available today on the market. And this creates an extremely stable platform that is also critical for our software AI stack, because when you have clean, jitter-free data that you can reliably use for machine learning, you can dramatically improve pointing accuracy, perform health monitoring, and run autonomous operation with confidence. And so our ultimate goal here at Magma is to partner with bus manufacturers and provide full mission capabilities to enable the most ambitious and challenging mission, both at commercial and national security standpoint. Could be around Earth and beyond Earth, geo. And so think about packaging the performance of the James Webb telescope with the intelligence of a Waymo car, but in a small form factor at a fraction of the cost that the primes would charge. That is really our goal and what we're excited about.
Okay, and so these jitter or micro vibrations, I think was the other word, issues. I mean, I assume this has been pretty much around since the first satellite, so to say.
It is.
basically, like over 60 years. And so,
And the technology has not really changed, really.
yeah, so that was my next question. So like, this sounds like it sucks. Like you said, it has sort of follow-on effects on like communications and imaging and everything. So how have people dealt with it? They just accepted it, or like has there been like you just I think you just said technology hasn't changed at all. Is that true? Has there not been any attempts?
So
Maybe they failed, or
yeah, so for the last 10, 15 years, I would say the level of stability and pointing accuracy was really just a problem for NASA or maybe exquisite military missions. But like today, you look at what is going up and what is going to go up in the next few years, and you can understand that vibration is becoming more and more of a problem for also commercial applications. And so before you spend a lot of money into isolation platform, trying to mask or filter vibrations, and that's kind of like it's usually a band-aid solution, like trying to, after you design your mission, you try to figure out how to reduce vibration. And not easy. Like NASA spend hundreds of millions of dollars to try to figure this out. And so what we are doing here at Magma really is to remove the problem at the source. So we remove the ball bearings, which are tiny, components within the reaction wheel they suck. They've been around for, as I said, 50, 60 years in spacecrafts. And what we're trying to do really is to make it much easier to achieve the level of stability that you would like to have without need to add more complexity and isolation system to your mission or to your satellite.
and so you mentioned they're like exquisite missions, right? And I know what you're thinking of, but like if I think in the military domain, and you mentioned communications and optical communications, right? So we have the SDA, what's it called? The proliferated warfighter space architecture, right? Which is supposed to be all optically interlinked. So this seems very relevant. So, and then on the commercial side, Starlink satellites are optically interlinked, right? So are there solutions, but maybe like they're just solutions primarily for these exquisite things and they're just too expensive? Or
no, I mean, absolutely. I mean, it's a great point. A lot of investors, of course, ask that question, right? Like Starlink already is working. Why do you need what we are building, right? It all comes down to the fact that you can, if you want to push more data through laser, you need to be more precise because when you are more precise in pointing at other satellites, your beam can be narrower. You can pack more data, more energy, and so you can achieve, hundreds of gigabytes, if not terabytes, of data. So it all comes down to capacity, right? So Starlink has, 20 something gigabytes per second, which is good for what they're doing. But if you want to pack more and more data, you need to be more precise. And so we are really trying to increase the number of the capacity of a satellite by not having thousands of satellites, but you can achieve the same bandwidth with much less smaller number of satellites because you're more precise in pointing and you can pack more data into it.
And so that would also seem relevant if like this is like we all know this is like for better or worse one hot topic at the space community right now is like ultimately having like orbital data centers. So that seems like it would be relevant probably for that as well.
100%.
Okay.
Yeah.
Okay.
Yeah, absolutely. I mean, if you think about, how fiber optics today work, right? There's a lot of data going through cables underground on the ocean, and each fiber optic can achieve even terabytes of data byte per second. In space, we're talking about tens. So you can understand there's a lot of way to go. We can push way more data through laser. And so what we're building is going to be critical to achieve that.
Okay, so now we kind of ended up talking a little bit about communications. Quickly on the other sort of you mentioned imaging, right? And sort of I guess that would be about increasing resolution. How should one imagine the sort of benefit there, and is it quantifiable, sort of like, oh, your spatial resolution
so it's not
by
resolution
X%, or the satellite can be smaller or whatever?
So the resolution itself is dictated by the camera, so the lenses, etc. What we're gonna improve is the sharpness. So let's say you have a 10, 20 centimeter resolution, but the image is all blurry. That's kind of like useless to you, right? You want a 10, 20 centimeter, but you also want extreme sharpness and contrast so you can see a 10, 20 centimeter resolution. So what we're providing really is the tripod for your camera, right? So when you're taking a picture at night with your, stargazing, and you're trying to look at stars with your telescope, if you have some enthusiasts, I would imagine this podcast are stargazing people. Well, you need your tripod to hold your telescope, because otherwise any vibration might affect the way you collect data, you take a picture. So that's what we are. In a nutshell, we are the tripod for a camera. and so that you can improve the sharpness and the quality of an image. And that's really critical because, again, you can have a pretty picture from far away, but if you want to see a car or you want to see people, you need to have enough sharpness to see cars and people and see what they are. And so that's what we can become really critical. And we're talking to the DoD, NRO, we're talking to the organization that do require high level of, crisp image sharpness and crispness. And so, so that's really exciting. That's why we are critical. We're not doing the sensor side, we're doing the support of the sensor.
Okay. And so, I'm taking a step back. How did you and your co-founders maybe wake up one day and decided like satellite jitter sucks, let's do something about that? How did that all happen?
Yeah, so I make this joke often, and I'm sorry if the listener really heard this, but my last name is Stabile, right? So all of a sudden I found myself in my PhD dealing with stability, and I thought, okay, this must be my calling, and I really love it. I mean, I went to the UK for my PhD, and I was asked by the European Space Agency, UK Space Agency, to really deal with this issue of satellite vibrations. And so during my PhD, I developed this bulky, high performance, but still bulky isolation platform. And when I moved to the US in 2019-20, I thought there must be a better way to do this. And so I pitched to NASA the idea of removing the ball bearing and using magnetic levitation. They liked it, they gave me some money. And I started by myself. I was in a one-bedroom apartment with my wife during COVID. I had to rent out equipment. I have a picture of me on the hallway, having bungee cords hanging from the ceiling, trying to do tests. But those tests were really positive, and I got the phase 2. And then with that, I was able to hire people, get an office, get out of my apartment. And then I met my co-founder, Jordan, in 2022, and he was trying to deal with the same issue of satellite vibration. So we clicked, I brought him in, and ever since we are a dynamic duo, unstoppable, as they say.
Okay, so now that you made sort of that joke about your last name kind of being the, kind of stability, I'm like shocked you didn't just call it Stabile Space.
I'll tell you this,
Magma Space?
For some time I was thinking about the reaction wheel calling Stabilev, Stabile levitation, but then I thought it sounded too Russian. I said, okay, no, maybe not good. But otherwise, I do think about stuff. Yeah, of course, I was trying to play on my name a little bit, but I thought it was a little bit too cheesy. And okay, let's get away from it.
Gotcha. Okay, so let's kind of make this a little bit more specific. What is the sort of, how should listeners imagine the actual product you put in a customer's hands? What did you get?
Absolutely. So at the beginning, our goal is to sell drop-in, plug-and-play reaction wheels as the way you would buy from, Rocket Lab or Blue Canyon. And so they don't need to change anything on their satellites. The idea would be you plug it in, and all of a sudden you have 95% plus vibration reduction. That's the easy, immediate benefit that they can have.
Okay. Just kind of quick follow-up question on that. So you say like not changing anything on the satellite. I just want to like no different, I don't know, volume, mass, power requirements, or
there is a little bit more 20-30% more volume, and also 20% more mass. But the advantage for us, because we eliminate the friction, you can push the wheel at higher performance, and so you can have more momentum and torque.
Okay.
And also higher reliability, because ball bearings are one of the main things that fail in satellites. And so by removing the ball bearings, now you can also increase your reliability of the whole satellite, which is an important factor for commercial, especially because, every year that you can still generate revenue, it's a year that you can create profit, no?
Wait, I didn't know that ball bearings are a frequent point of failure for satellites. Is that
pretty often? Yeah.
Like, and it's sort of like, so you're saying maybe you have a satellite that you think would have been there for like 10 years, and then suddenly after 5 years the wheel breaks?
Even less. Yeah.
Really?
Yeah.
And then the satellite can be, depending what your mission is, the satellite can be useless after that, right?
Absolutely, and that's why.
Wow.
That's why there are missions that fail because of reaction wheel getting stuck. Primes pay big bucks to Honeywell to get their wheels, but even Honeywell has problems. So reaction wheels are a known failure point. And so imagine if we go into the moon and going to Mars, right? You're a E2MC, right? You want to go to Mars, but you need to be reliable for like 10 years at least. And having ball bearing is a really risk of failure.
So, okay, I'm kind of making this up as I'm listening to you, but I imagine this could also be like a double-edged sword in the sense that, like, if you have a very critical mission, right? Maybe the typical customer reaction would be like, yeah, I think you mentioned Honeywell as an established supplier. Honeywell, it's probably really expensive, but we know it's like low risk, and it's like, oh, this Stabile guy, like yeah, last name sounds great, but we don't actually like we haven't seen this technology like hundreds of times and 10 years in space. Like, do you get that reaction from customers, and then
Yeah, I mean,
how do you deal
of
with it?
course, space has a lot of inertia, right? Space doesn't, that's why things have been the same for the last 50, 60 years,
Yeah.
because people know what works and they just stick to what works, right? So it is for sure one of our challenges, right? To educate and convince customer. But for us, having the support of the DoD that really helping us to prove and go to space, and you guys through the Orbital Edge, through the ISS tech demo, I think those are important steps for us to show, that the tech work, that is reliable, and it can perform as good as we think we can perform. So yes, absolutely, we need to go to space, show heritage, and we have in plan several missions in the next couple of years to show that.
Yeah, that was my next question, sort of how you are structuring basically the go-to market. So you want to talk a little bit about how you guys are doing that? If you can talk about it, who are the first customers? What the first missions look like?
Yeah, so absolutely. We have the advantage of our technology is really kind of pervasive, right? We were talking to customers that are doing imaging, laser communication, power beaming, in space manufacturing, and so the goal for us is to sell it as a higher upper tier reaction wheel to bus manufacturers that are out there, both in Europe and in the US. We are not ITAR, so we can sell also in Europe. And so the beginning would be a supplier to the high performance missions that, especially when you talk about SDA tranches, right? We can be a differentiator for all those tranches, especially when it comes to missile tracking, missile warning, data through laser. We could be an extremely critical components for all these platforms if they want to win the SDA tranches. So definitely for us is going down the road of the SDA and the DoD and show that we can achieve the level of performance that they want. And on the commercial side, we are talking to, as I said, power beaming companies that want to try us and do a tech demo with us. In space manufacturing is really interesting, actually. When you do pharmaceutical or semiconductors or fiber optics in space, you need really low level of vibrations. Otherwise, you have a lot of defects. And so it doesn't make sense, right, to build something in space with defects. You want to have the most pristine outcome. And so those platforms will be really critical for them. And we're really excited to partner with some of those companies. We will announce soon, but yeah, there's some work going on for that.
Okay, and so your first missions what would you actually do?
Would be either imaging or laser communication. That's what we're trying to work on. The one that is more like immediate, while doing tech demos for power beaming in space manufacturing.
Okay, gotcha. And you mentioned that selling to the bus manufacturers. And so what does the decision-making process and something like that actually typically look like? Because the bus manufacturers obviously then have like an end customer, right? Unless they're kind of what some, I guess, satellite companies are starting to do now, like Apex apparently, is actually produce satellites and put them on the shelf, which is kind of also very interesting. But question being sort of like, who drives the decisions? Like, do you still have to convince the end customer, or is it enough to convince the bus manufacturer?
So usually when a customer orders a satellite, they asking for a certain amount of maximum jitter. It's called jitter budget. And so the satellite manufacturer needs to figure, okay, what produces jitter? Okay, reaction wheels, solar array drive mechanism, antenna pointing mechanism, etc. All of them build up to the level of jitter. And if they are past the jitter budget, they need to figure out, okay, how do we reduce this? And that's when you need to think about isolation platform, or maybe remove some of the components, etc. So we will be a way to help them to meet this budget, because all of a sudden we are not the main source of vibration. We actually are the least source of vibration compared to other components. And so that's the way we're gonna sell it is like, we're gonna be critical to meet your jitter budget and simplify the way you design your satellite. Because as I said before, sometimes you need to go on the satellite bus afterwards to fix the issue of jitter, and you need to kind of like scramble to think, okay, how do we do this, right? Because it's really complex to remove vibration. So for us, it simplifies things because, again, we remove the problem at the source. And so that means you don't need to add more complexity in isolation platform. That's the way we're we're framing it, and that's the way we're talking to companies about.
Okay. We're crossing over a little bit in the technology because we have to be careful because it's supposed to be a non-technical podcast. So no throwing around mathematical formulas, please. But let's take a step back, and it's my job to ask the stupid questions. Like, what actually causes the jitter? Like, what are the main factors that cause jitter?
Yeah, so in ball bearings have micro defects on the balls and all the components, and when these things spin, all these defects produce tiny vibrations, and because reaction wheel always spin, they always spin on the satellite. They're always producing those vibrations, and so that's why when you remove those ball bearings, all of a sudden you don't have that issue anymore. And so the ball bearing is usually one. Stepper motor could be another one. So the motor that drives the solar array or an antenna mechanism can also be a source of jitter. But usually the ball bearings, because they spin all the time in reaction wheels, are the main source. And so I remember if I think when I started thinking about magnetic levitation, I tell you this, I was in a conference in Europe during my PhD, and half of the presentations were about ball bearing and how to simulate ball bearing and how to improve the ball bearing. It was so boring. And during that conference, I thought, this cannot be real. That like a lot of these people are working on these tiny things. They don't really reach a plateau on what we can do. And that's what I started thinking about magnetic levitation. So it's a complex problem. A lot of PhDs are working on it right now. And it's still really difficult to solve at the ball bearing level. So that's why I thought the solution that we come up with is innovative, and it reduces the issue altogether, remove the issue altogether.
And so we've been kind of tossing around magnetic levitation, but can you kind of go one layer further down and try to, again, without formulas, illustrate how that...
I don't know if you ever seen on YouTube when they have superconducting material, they put like nitrogen, liquid nitrogen, all of a sudden this pack of superconducting material floats on the magnets. And that's, it's levitation using superconducting materials. They don't need any power, but of course they need to be cold, right? In our case, we are not using superconducting materials, but we are emulating superconducting materials. So we are emulating the behavior in superconducting materials without the need to go cryogenic. So that's why it's a different way of doing as it was done in the past. We don't need a lot of power. It's a really simplified control. And that's why it can be done now in space versus what they tried in the past, where it was really power hungry and a lot of computational effort to levitate this disk in all directions. We simplify this behavior dramatically. And so that's why now it doesn't become a burden on the satellite to have magnetic levitation. That's kind of like the critical element of our technologies, emulating superconducting material without growing cryogenic. That's the key.
Okay. And so as a result of the levitation, stuff doesn't touch other stuff. And so that's, like you said, stuff that has irregularities doesn't touch other stuff that has irregularities, and hence you don't have jitters because the magnetic field, so I'm really not an expert in magnetic fields. It's kind of like smooth. There's no like irregularities in the magnetic field, so to say that can, okay.
Yeah, and then of course, one question could be, are you affected by the Earth magnetic field, right? But Earth magnetic field is really tiny compared to the magnetic fields that we have inside our reaction wheel. So the effect is really minimal. And on the other way around, if the reaction wheels start generating torque, is not the case because we shield the wheel, so the magnetic field doesn't escape our reaction wheel.
I was going to ask that because there's obviously like electronics and other stuff on the satellite that doesn't get affected by your.
Of course, that's why we shield our structure, our reaction wheel, so that the magnetic field is nicely contained, and it doesn't affect other components, like you said, or other payloads. Absolutely.
I assume that's something you have already tested, at least on the ground.
Yeah. So magnetic cleanliness is always one of the questions that we got. So yes, we already have simulations and tests on this.
I'm learning like a number of new words I haven't known existed, like magnetic cleanliness.
Cleanliness, yeah.
There we go. And so what TRL level would you say is this now?
Yeah, we are at TRL 6 for the magnetic levitation, the magnetic bearing. Soon to go on in space in 26. We have a couple of opportunities, one in February, and the other one in Q4 on the ISS. So yeah, we should soon go to space. We are trying to talk to different companies to have other hosted payload missions. And so we'll see. We'll try to maybe either add another one in 26 or do one for sure in 27. But that's kind of like where we go into space and increase our TRL. Also, I want to make sure I mention that this magnetic levitation, now we're using for reaction wheels, but we're also thinking about isolation platforms. So one thing that we are extremely interested in is having a platform that you put a payload on top, let's say a camera or laser terminal, and this platform is, let's say, grounded on the satellite where you don't need it. And when you need it, you levitate the platform enough to isolate yourself from the rest of the satellite. And now on top of this platform is extremely quiet, right, stable. And so you can do imaging, you can do laser communication, quantum sensing. And this is something we are really excited, and it's going to be the same technology that we are validating now. So that's, we are working, we can use the same concept of magnetic levitation both for the reaction wheel and for this isolation platform.
And so as you're about to soon go and test this in space, I mean, is there anything that keeps you up at night in terms of like the technical side? Something like, oh, not sure this is going to work, or this is the one I'm least certain about, or?
I mean, of course, because space, here on Earth, gravity, right, is a constant force that you need to fight. And so the levitation on Earth is different than levitation in space. And so until we prove it fully in space, of course, there's always going to be uncertainty. We do simulation, we've done parabolic flight, we're going to do more parabolic flight. But of course, we want to make sure this works exactly as we have simulated and tested here on Earth, also in space. And of course, the other thing is space is slow, right? Like you need to deliver something today that's going to be launched in 7-8 months. And so that cycle, of course, is tough on a small company like ours, where we need to develop something quickly and then wait to know if that works or not. So we are already working on the next iteration, but you can imagine that you don't know for sure if what we launch work exactly as expected, or if there are some things that needs to be improved and you need to wait and learn to improve in the next iteration. So that's definitely the things that keeps me up at night, is the slow cycle. And I would like to learn faster, but it's a limitation on space. And the transport, there are amazing opportunities, right? But there are only 4 a year, 3 a year, and hopefully there are more launcher coming up soon. But it is a limitation for all of us.
Okay, but let me ask the other way around. So let's say you go to space, excuse me, and then you go to space again, and then actually it works. Like people can see, like, okay, it does what it says it would do, and so forth. And suddenly you get like many interested customers. How difficult is it going to be to like scale this? Is there like, can you set up a factory and just do many of these, or is there any like sort of like bottlenecks?
Yeah. So at the beginning, our goal is to mostly outsource most of the manufacturing and then do the final integration testing in-house. As we grow and we continue fundraising, we will bring more and more components in-house to reduce our costs and increase the margin. But the most critical component for us is our magnets. Not because they are expensive, because magnets actually are really cheap at the moment in China, but because they're mostly made in China.
That's what I was getting at. Yes.
It is a big concern, not just for Magma, right, but for the whole Western world. I see the US is putting money into developing more factories. Europe has some, India has some others. So at the moment, it's not an issue. We order 800 magnets and we got it custom magnets we got after 4 weeks from China. But of course, there's always something we need to keep in mind.
Yeah. So let's actually, because it's interesting, I think it's worth opening like a 2-minute bracket on that, since you're like the right person who can talk about it. Is like, why are all of the magnets coming from China? Like, why can't we have like an American magnet company?
So the misconception is all the material is in China, which is not true. The raw material is distributed all over the world. China had the foresight of making these factories 20, 30 years ago, and now they have so much know-how and they have perfection all the manufacturing that they can make, as I said, 800 magnets, and it costs custom made $2 each, and we got it in 4 weeks. In Europe would have been 3 times the price and longer lead time. They figured out the way to manufacturing fast, and they have a lot of technicians. So in the US and Europe will take some time to catch up, just because you need to build the know-how and the technical skills, because the magnets are made in a certain way that is not like CNC machining is a little bit different, and you need expert technicians and machines to do that. And so I think it will happen, because we've been blind for a long time, thinking, yes, let's leave everything to China, but it was not clever from the Western world to do that. But now we are definitely catching up, and it's going to happen. It just will take time.
Okay, yeah, I'm sure there's some hard tech entrepreneurs somewhere in El Segundo or somewhere.
I thought about that too, myself. I was like, why don't I start making my magnets? I mean, it seems like a great business. Not fancy, but like definitely a great business.
Yeah, yeah. And so, okay, and then taking a step further, so like let's assume magnet problem, supply chain problem gets solved. You can actually scale up. Where do you see this going? I mean, should we imagine, do you see this substituting like all existing wheels, or is this going to be a certain niche, or like how should one envision that?
I truly believe that we can become the new standard. I mean, there's nothing crazy about what we're building. It's not the cost can be reduced dramatically. I do believe, like, why having ball bearing and risk, the vibration, the launch failure, the failure to mission, and not having maglev technology. I feel like that's going to be the future. We're the only one at the moment, but I'm pretty sure some will come up as soon as we show this. But I do believe that it will become a new standard. But of course, I don't want to say that our goal is not to become a component just company. We want to really take on the full mission capability. As I said at the beginning, we want to partner with bus manufacturers and really kind of like build a satellite for high performance, high stability, high pointing accuracy missions. And not every mission requires it, but a lot of missions do require it. And what we're looking right now is quantum. There's a lot of, you probably saw IonQ, right, doing some moves in space. Inflection just announced the partnership with Voyager. Quantum is happening, not quantum computing, but quantum sensing and quantum clock is happening in space. And for all these quantum technologies, you need extreme level of stability. So we believe that we're going to be extremely critical for having quantum sensing and quantum GPS alternative in space, and we're really ready for it. We want to talk to quantum companies. We do believe that our technology is going to be the key to make it happen.
Yeah, well, IonQ just bought an optical communications company, kind of coming full circle to where we started. So that's
absolutely.
Like a relevant potential customer for you. Yes.
Yep.
Okay. And so again, if everything works out, like 10 years down the road, like you kind of started talking a little bit about it, but what's your vision here?
I think I want to, I want to be a critical aspect of thinking that Magma was instrumental to push humanity and satellites towards like Mars and the moon. Because really, if you want to go to Mars and the moon, we need high precision, we need high performance, we need reliability, we need autonomy. These are all the things that we are building. We are really building the muscle and the brain of a satellite. And we do believe that this is going to be critical to go beyond LEO and GEO. And so I'm really excited about it. We are collaborating with a company who's doing power beaming ultimately on the moon. I think that's a really exciting, critical to have life and missions on the moon is to pass the lunar night, right? You have 14 days of sun and 14 days of darkness, and so you need to get power in some way, and power beaming is one of them. And we are excited to working with this company and to hopefully show that we can have a constant presence on the moon.
Actually, I should have asked this before, but I didn't pick up on the power beaming. So for like the optical communications, I can see that you don't want to lose. I mean, even slight jitter, probably you start losing information. But for the power beaming, what's that about? That's like you would kind of
efficiency, right?
Power efficiency, okay.
Efficiency, because of course, the more you can stay on the target, the more power you can convey. Think about the beam. The tighter the beam, the more energy is concentrated, right? So the more you can stay on target, the more you can transfer energy. And then in reverse, the more energy you can transfer, you can make smaller solar arrays, right? You can have smaller batteries. It's all linked, even less energy lost on the satellite through heat. So pointing accuracy is going to be extremely critical with all these power beaming companies, and we are ready for it.
And I assume like the longer the distance, the worse this get, or
the more dissipate. Yes, of course. And when you were talking a few episodes ago about like power to ground, and they were talking about 10 meter radius. 10 meter radius means that if the target is in the center, most of the energy can be lost because of the beam width, right, at the on the ground. The more tighter you have, the more signal to noise ratio you have. And so again, even for communication can be really critical because you can pack more data, you can make sure you don't lose packages. So power beaming and laser comm are going to be critical. Like they will need what we're building for sure.
Okay. I myself said we shouldn't do any formulas, but just out of interest, sort of like the relationship of sort of like, roughly speaking, like the jitter and sort of like, whether it's efficiency loss or information loss, is it sort of like linear or is it worse? Is it like quadratic, cubic, like?
I mean, it could be, it depends how bad the jitter is in the end, but you can lose 50, 60% of the energy just because of jitter. I mean, it can be kind of a lot. And again, it depends on different factors, but the jitter is like, think about, you're pointing your laser pointer to something and your hand jitter, you can imagine, put that now at a distance of hundreds of kilometers and you're trying to target a ground station or a solar farm. Well, it's going to be, it's going to be tough to be precise.
Okay, gotcha. Okay, as we're coming towards the end here, maybe a few sort of final questions I want to ask you. One, we do have a few minutes time if you want to talk about sort of orbital edge. I mean, obviously, I'm very biased here. I mean, in case the listeners don't know, E2MC is one of the founding partners of what's called the Orbital Edge Accelerator, jointly with our government partner, ISS National Lab, which we're very happy with, and then two other investment firms, Stellar Ventures and Siri. Yeah, if you want to kind of
we just wrapped up,
and feel free to give critical feedback as well.
We just wrapped up this program a couple of weeks ago in San Francisco. The demo day. We're 6 companies, amazing cohort that you guys selected. I think it was a really good program for different aspects. One is the investors like you guys are space focused and space. You understand what it means to go from prototype to space and to scale the technology. So I think that's important for us. And also the level of mentors that you gathered and the support from the ISS National Lab was invaluable. So now we have this opportunity with the ISS National Lab and the ISS to launch in Q4 26. And we're really excited because it's going to be 6 months of continuous testing for us, gathering data, showing, being outside. We will be outside the ISS, so with vacuum and cycles of temperature. And for us, it's going to be extremely important because, as we mentioned before, heritage is everything for this sector. And so showing heritage is going to be critical for us too. So I think it was the first cohort, right? So of course, stuff that can improve, but I think overall it was an amazing program and I highly recommend it for the next. I think you guys have it's open for the next cohort, the call, or not yet? Or
not yet. I think that'll probably come out in late February, early March is my best guess. But
if anyone has any question about it, like please reach out and I'm willing to talk about it.
Cool. No, thank you. And it was fun having you in the cohort and happy
thank you so much.
Enjoyed it. And another question is, so usually when we invest startups, very often they're sort of like San Francisco, LA, Colorado. You guys are in DC. How's that?
I found myself in DC. Just my wife moved here, and I followed her in 2019, late 2019. Then COVID started, of course, and I'm stuck here. I'll stay here. But to be honest, I was skeptical of DC because I thought, space is in LA, space in Seattle, Denver, Florida. But soon I realized there's a lot of space here in the DMV, right? The District of Columbia, Maryland, Virginia. And so I'm going constantly to, events and talking to military people, stakeholders. I feel like actually it does make sense for us to be here. I've met a lot of investors are moving here to the DMV, like you guys. And so now that I've been in DC for 5 years, I actually believe that it was the right choice, and we have a lot of support. And I would like to grow the company in this area. We're talking to DC to try to get support, but we'll see. We'll see how it goes. But I feel like everyone should have a presence in DC because that's where decisions are made and the money is, right, with the Pentagon and Congress. And as I said, a lot of investors are moving or have a presence in DC, so it's becoming really relevant for the space sector and the dual use, right? Dual use technologies like ours.
Yeah, again, it's another one I'm biased on because E2MC is based in Arlington, Virginia, as you know, right? But I think it's a very dynamic ecosystem, and like you said, at the end of the day, a lot of the relevant decisions and a lot of the money is there. So
Absolutely,
very, very relevant for space. Alessandro, final question, always the same: science fiction. Favorite science fiction?
Yeah, so I am a big Andy Weir fan, but unfortunately last time someone mentioned Project Hail Mary. So I will mention a book that is less known, which is Artemis, which I think is really interesting, is a city built on the moon, which seems really relevant right now. And, bustling city with thousands of people that were born there, and they're mining, of course, on the moon. And there is some mystery, some Brazilian mafia for some reason. But
Okay.
it's a really interesting book, and Andy Weir always uses engineering with humor and more normal terms. So I think that combination, is always amazing.
So, that is an Andy Weir book as well.
It is
Okay.
a less known out of the three. The Martian.
That one I didn't.
Project
The other
Hail
ones I've
Mary.
read. This one actually I didn't even know existed. So I look it up. Now you got me very. I mean, I'm
Yeah,
also
I mean, Project Hail Mary.
I'm also Brazilian. I'm very interested about the Brazilian mafia.
Yeah, why did it choose Brazilian mafia? I don't
The
know.
backstory
But
there
it
is.
is. As an Italian, I say maybe we pass it to you guys. I don't know.
Okay, Alessandro, thanks so much. Good luck with Magma, all the exciting things you have going on there, and the in-space demos and so forth.
Thank you so much for having me. This was fun, and I'm hoping you learn a lot from terms from me. I hope also the listener learns something from Magma for what we're doing. But yeah, really exciting. Thank you so much.
Yeah, listeners, remember jitter budget and magnetic cleanliness.
Cleanliness.
Thanks, Alessandro.
Bye.
And that's it for another nominal episode of the Space Business Podcast. And once more, if you enjoyed this episode, please leave us a 5-star rating on your favorite podcast platform, such as Apple or Spotify. You can follow us on Twitter at podcast_space. We're also on LinkedIn under the Space Business Podcast. Lastly, if you have any feedback, including ideas for guests, and that may even include yourself if you have an exciting space story to tell, or interested in becoming a sponsor, or really for any other suggestions, you can drop us an email at spacebusinesspodcast@gmail.com. Thanks so much for listening, and see you for the next episode.